Last time we looked at a change in coordinates in a single integral, a double integral, and then a triple integral. In the single integral case, we do as we always do with u substitution from Calc 1, and to compute the change in the differential unit dx, we take a derivative of the conversion equation. For polar and spherical, we had sort of previously memorized what to do with the differential unit dA and dV. In the case of polar, we included an extra r, and in the case of spherical, we included an extra rho squared sine phi. I made the observation that the r and the rho squared sine phi could be obtained by taking the absolute value of a determinant built from the partial derivatives of the conversion equations. What I want to start with now is an explanation of why that's the case. So I'm going to sort of produce this differential unit that goes into an integral, at least in the double integral case, in the general setting when I'm converting from the old variables x and y over to new variables u and v. So the analogy that I'm going to be making the whole time is that with Calc 1. So keep in mind, like, if you were doing a u substitution in a single integral, maybe like u is 3x or something like that, then I wouldn't usually set it up like this, but that would be exactly the same thing as saying x is 1/3 u. And so like if we write the old variable in terms of the new variable like this, then we can see that dx, the differential unit that's in the original integral, gets replaced with a 1/3 du. That's the new differential unit with like this fudge factor 1/3 that goes into the new integral. Okay, so for a double integral, I want you to imagine that we have an original integral set up in terms of x and y, the old variables, and I know the conversion equations for x and y to the new variables u and v. And you can think of a familiar situation where we have this. If you're converting to polar, for example, these are your conversion equations over to the new set of variables. Your old variables are x and y, and you have each of the old variables in terms of the new variables r and theta. And we know that in that situation that dx dy gets replaced with r dr d theta. So the general context is this, and what we're after is what do we replace dx dy with in general if I have x as a function of u and v and y is also a function of u and v. So it's sort of question mark du dv. So this will give us a general technique for converting integrals. And the thing that we come up with is going to be good for integrals of any dimension. So you can do triple integrals with this as well. Okay, so this is the situation. I have two coordinate axes here set up. I've got a uv axis and an xy axis over here. The xy are the old variables and the uv are the new variables. And just like I had up here, I have the new variable in terms of the old variable, and I want to know what the effect, or I kind of want to write the change in the old variables in terms of something times changes in the new variables. I hope I said that correctly. So let me come over to the UV plane and imagine that there was a small change in U and a small change in V, and see what effect I have on the change in X and the change in Y. So changing U and changing V slightly produces a little rectangle in the UV plane, and it might produce some sort of contorted shape in the XY plane, and that's through these functions G and H. So to help me sort of take care of all the notation, I want to imagine, since X is a function of U and V and Y is a function of U and V, I want to imagine a vector function which accepts the variables U and V and basically points at the appropriate xy point in the xy plane. So this is going to have x coordinate GUV and y coordinate HUV. Okay, so like at U naught V naught, which is the corner of the orange rectangle, the vector function is pointing at x naught y naught. And then as UV varies within this rectangle, the RUV varies within this, whatever this shape is. Okay, now that we have that notation, imagine taking the U variable and just moving it ever so slightly, like delta U. Then along here, it would look like I would move along the bottom side of this rectangle, right? But over here, it looks like when I move the u, both the x and y coordinate move, and it sort of travels along this lower edge, like that. So if I move the u value, a full delta u, the x and y coordinates are going to move from this corner over to that corner. Well, using the vector equation, I can estimate that movement from here down to that corner using a partial derivative. So let me try and get it drawn properly here. This vector right here is an approximation to the difference of RU naught V naught, which is X naught Y naught, and whatever the RU value is over here. So if I take the partial with respect to U and multiply it by delta U, I get a vector that approximates the connection between that point and that point. And similarly, if I move V ever so slightly, delta V, then the R sub V vector. Okay, now if I'm interested in the change in area that results from adjusting delta U and delta V in this manner, then I can use a fact from the cross product section that says that the cross product of these two vectors in magnitude is the area of this parallelogram right there. So let's write that down. Okay, let's try and expand on this a little bit further. So the R sub U vector is the partial derivative of this vector function with respect to u. So it's going to be the partial derivative of the x component with respect to u and the partial derivative of the y component with respect to u. And since these vectors are in the xy plane, the z component here can just be assumed to be 0. So let's write this out. Okay, so expanding this cross product, clearly I'm going to take the last column to do the expansion, and I just end up with k times the determinant of this little 2 by 2 times delta u times delta v. The determinant of this 2 by 2. Okay, and the area is the magnitude of this. So this is a vector at the moment. The area is just this scalar component that's out front. So the determinant of this matrix times this scalar bit right here. So the area is, I have to put an extra bunch of magnitude signs on that to be formal. Okay, so it turns out that this right here is called the Jacobian of this transformation. And typically we reverse these two components. We put the x's along the top and the y's along the bottom, but the determinant of that matrix is exactly the same. So we say that the Jacobian of this transformation here, so it's the determinant of this matrix involving the partial derivatives of the transformation, and the notation we give for this determinant is partial xy partial uv. So it sort of captures the derivatives with respect to the old variables with respect to the new variables. Or sorry, I might not have said that right. The derivative of the old variables with respect to the new variables all sort of combine into this little box. And so it turns out that what we've discovered then is that the differential unit delta A that helps us form the double integral is basically the absolute value of this quantity, because the area is positive, times delta U delta V. And that's exactly what we are after. If our old area unit was dx dy, then this is the computation we need to put when we're converting the double integral over to our new variable set. And it was this computation that we got for polar exactly, and we got it for spherical as well. If you take the determinant of that matrix with the partials, then you get exactly the fudge factor that you need when you go from the old set of variables to the new set of variables.